Thanks so much to the organizers for inviting me. So I'm going to talk about something that's sort of directly related to sparsity and compressed sensing and imaging. So let me just try to motivate the problem first. So just to kind of get some notation sorted away, this is the sort of standard compressed sensing problem. So we have a signal X, which the signal is not necessarily sparse. It's something like an image. We measure it through some linear system phi, which is typically compressible. So we'll assume that the signal dimension n is larger than the measurement dimension m. And we have some sort of additive noise. We're going to take the sort of classical approach in compressed sensing. We're going to minimize some sort of penalty or regularization subject to some constraint on the measurement fidelity. And we're going to assume in this talk that we know something about the noise level, which allows us to choose that measurement fidelity parameter. And the main question that I'm interested in for this talk is how do we choose this penalty here? Okay, so typical choices of penalty. In some sense, okay, so we're going to now assume that the signal X is not necessarily sparse, but we're going to suppose that there's some analysis operator, which I'll just loosely call a dictionary. Really, it's the sort of pseudo-inverse of a dictionary, but there's some analysis operator, psi, and we're going to assume that the psi times X is going to be sparse or approximately sparse. So this could be something like a total variation or something like a wavelet transform, something like this. And for now, we're just going to assume that this psi is fixed. So a typical thing is if we knew that psi x was completely sparse, then we might want to minimize this the counting norm, L0 norm. But the problem is that this is an NP-hard problem, so we typically don't consider this. So what most people do is they'll consider the tightest convex relaxation, which is the L1 norm. And then for this problem, there's all sorts of fast algorithms that can solve it. And we're not going to really concern ourselves too much with the particular algorithm in this talk. I think in the simulations we use Douglas-Rashford splitting, but we'll just stick with that. And I'll just note there's many other things we could do as well. There's penalties based on the p norm for p between 0 and 1 and so on. But we're going to focus sort of on this style, this convex style of penalty. All right, so here's the main question. How do we choose this analysis operator, this dictionary? So maybe we might want to choose a wavelet dictionary, but there's many wavelets to choose from. So how do we select among those possibilities? Maybe we can actually take a whole bunch of different dictionaries and stack them on top of each other and get some sort of compound dictionary. You know, for example, maybe this is the orthonormal Dobeshi's 1, and then Dobeshi's 2, and Dobeshi's 3, all the way to Dobeshi's D. So that's one approach. And people have tried that. It actually works reasonably well. But here's the main question. What if the signal is more sparse in one dictionary than another? How can we exploit this? Is there a way of exploiting this? And that's sort of what the talk is about. Okay, so here's just an example. We're going to take, this is an MRI image, and actually it's actually an MRI scene. It's a movie. So it's a three-dimensional object. There's two spatial dimensions, horizontal, vertical, and then there's a temporal dimension. And we're looking now at a one-level, undecimated wavelet transform of this. And so here we have like horizontal, vertical, and temporal. We have like low, 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 high, low, 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 high, low. And the point is that when you look, so this is in the image domain, and this is in the wavelet domain. So this is what comes out of that analysis operator. And you can see that depending on which one of these subbands you look at, things can be not very sparse or very sparse. Okay, so here's an example where you could think of each one of these as a subdictionary. And now what we notice is that the signal is much more sparse in certain subdictionaries compared to others. Is there a way of exploiting this structure? Okay, so what we're going to do is to do this, we're going to consider what we are going to call composite L1 penalties. So it's going to be a sum of weighted L1 norms. And these subdictionaries here, Sahd, we don't really care too much what these are. We'll just say that they have unit norm rows. The particular choice depends on the application, and I'll show you a number of examples later. But these are, you could say, a number of hypothesized analysis operators where you think, well, my signal might be sort of sparse in this domain, might be sort of sparse in this domain, and so on and so on. And you just kind of collect them all together. And now the key is you want to weight them in a smart way. And the question is, how do you select these weights? So we're going to propose a way of actually learning them from the data. So we're going to recover the signal as well as tune these weights from the data. That's the whole point. So we're going to call that the composite L1 penalty. So we're going to come up with two algorithms to do this. One is what we call composite L1 minimization. And the second is an iteratively reweighted version of that algorithm that has a little bit better performance. And so I'm going to describe these in the sequel. So let me just show you the algorithms, and then I'll show you a whole bunch of interpretations for them. Okay, so let's just focus on these middle two lines. Essentially, this is this composite L1 algorithm, and it just alternates two steps. The first step is just this standard L2 constrained weighted L1 minimization problem. And then the second step here is kind of the key step. This is how those weights are updated. And what you see here is this is the signal estimate from the previous iteration plugged in down here. And for those of you who are familiar with iteratively reweighted L1 algorithm, famous algorithm, Candes, Wake, and Void from a number of years ago, this looks very similar to iteratively reweighted L1. The only difference, so if this was iteratively reweighted L1, instead of this being a L1 norm on a vector, this would just be an absolute value of a scalar. Okay, so in other words, if this subdictionary reduces to just one row instead of being a full matrix, then that is exactly the iteratively reweighted L1 algorithm. Okay, so this is in some sense a generalization to where this is an entire matrix. Okay, so the advantages of this is the computationally tough problem that we're solving here is in step 4. This is something that's handled by a whole number of really nice algorithms at this point. So we can essentially plug in whatever algorithm we want. We just put it in this loop. This particular algorithm can handle real and complex data. It doesn't matter. Okay, so this is the sort of simpler of the two algorithms. One comment is that in this case, we're going to assume that this regularization parameter epsilon is fixed. It's fixed given by the user. So this is a slightly more complicated algorithm now. There's 3 steps. The main difference in the first step is that in addition to these weighting coefficients, which we could say are interdictionary weighting coefficients, there's some intra-dictionary weighting coefficients. So this is a diagonal matrix here of a similar style that you would see in iteratively reweighted L1. And so essentially now what we're going to do is we're going to update both of those weights. So there's the interdictionary weights are going to be updated according to in some sort of maximum likelihood approach. I'll describe more about this later. And then these intradictionary weights are adapted using this approach that looks pretty much just like iteratively reweighted L1. Okay? So essentially there's sort of 2 levels of weighting. There's weights per dictionary and there's weights within each dictionary. Okay. And then the last thing I'll point out is that in this case, actually, even these regularization parameters epsilon here, these guys are also adjusted. So they're not specified by the user. You initialize them, but then after that, you actually optimize them as well. Okay. So, so interestingly, these algorithms work a lot better than standard L1 or iteratively reweighted L1, as I'll show you in some examples. So it's sort of surprising how much gain you get out of being able to tune these weights. Okay. Okay, so now I'll show you 4 interesting interpretations of the algorithm. So both of them can be interpreted from an optimization perspective as an MM approach, majorization minimization of a particular non-convex penalty. And the question then is, what is that non-convex penalty? Also as a particular approximation of L0 minimization. Also as a Bayesian estimation according to a particular hierarchical prior. and finally as a variational EM algorithm, again under a particular prior. So all these different interpretations lead you to exactly the same two algorithms. So you can view them from whatever background you prefer. So first I'll start with the very first algorithm. So from the MM approach, the non-convex optimization, what it's actually doing is it's solving this weighted log sum optimization. And again, if you're familiar with iteratively reweighted L1, then this is not so surprising. There you usually have an absolute value. Now we have an L1 norm. And if you want to make sense of this, well, what is actually going on? How can you interpret this? There's a nice interpretation as this parameter epsilon, which is typically a very small number, as that goes all the way to 0. Essentially, what we're trying to do is solve a weighted mixed norm problem. And the mixed norm is the L10 norm. So here, basically, we have, this is an indicator function that says when the L1 norm is larger than 0. And then this LD, this is the size of the D dictionary. So the number of atoms in that dictionary. So they're weighted by that. Okay. So this is the non-convex cost and then the kind of a interpretation of it. And so it's I don't know, it's sort of interesting. It's sort of like a dictionary-wise L0 norm. Okay. Now, from the Bayesian viewpoint, it turns out that we can view these algorithms as an MM approach to a Bayesian maximum a posteriori estimation problem. And in this case, we have a hierarchical prior. So if we condition on those interdictionary weights, lambda, then the analysis outputs are assumed to be IID Laplacian. Okay? But then the prior that we're going to place on those interdictionary weights is the Jeffreys non-informative prior. So you combine two of these things together, and you get exactly that composite L1 algorithm. Now, if you're not a Bayesian person, you're more of a variational person, you might say, well, what about a variational approach? So it turns out, so now what we're going to do is rather than treating these lambda as random variables, treat them as a deterministic parameter vector. And if you say, well, my data is IID Laplacian for some fixed lambda, and I'm going to then update lambda by the EM algorithm, or variational version of the EM algorithm, you actually get, again, the same exact algorithm, this composite L1. So there's all these nice different interpretations, everything coming together. Okay, so stop me at any point if you have any questions. Okay, so now let's go on to the second algorithm. That was the one that was the iteratively reweighted approach. And so rather than diving right into that, we're going to take sort of an intermediate algorithm. We're going to look at the real valued version of that previous one, and we're going to keep these parameters epsilon fixed by the user. So the user is going to specify these different regularizations, which prevent, essentially they prevent the denominators from going to 0. Okay, so for now these are fixed. And we're going to focus on the real valued case, because in the complex valued case, some of the expressions change. But in this case, what happens is we have this algorithm that iterates, again, between solving a weighted L1 problem and then adapting the interdictionary weights according to this equation here, and then adapting the intradictionary weights according to the sort of standard iteratively reweighted L1 approach. So this is this intermediate algorithm, and this has some nice interpretations. So again, it's a non-convex optimization problem. The cost function is a little weird looking. There's a log inside of a log and so on. So if we want to try to interpret this from the perspective of how is this related to L0, we can take these parameters epsilon, just make them all the same and take that to 0. And you get an interesting combination. It's the sum of an L0 norm and an L00 mixed norm. Okay, so in some sense, so if it was just iteratively reweighted L1, you would be essentially trying to minimize this L0 norm. That's the interpretation of iteratively reweighted 1 as epsilon goes to 0. But now, because we have this, these additional weights per dictionary, you get this additional term which tries to look at essentially the disparity in sparsity across dictionaries. Okay. So these are a couple interpretations from the optimization perspective. Now, from the Bayesian perspective, sort of interesting, we're now going to have, instead of IID Laplace, if I condition on those interdictionary weights, it's actually IID generalized Pareto. So that is a slightly different approach. And again, Jeffrey's non-informative for those. So you put these two things together, and you get exactly this map cost here. And if you instead prefer to do it from the EM perspective, where you think of these lambda weights as deterministic, then you could say it's IID generalized Pareto, and you do an EM-like optimization of those weights. Get the same algorithm. Okay, so the final thing is to generalize this a little bit, and rather than treating these epsilons as fixed and supplied by the user, we can optimize them as well. And so what we do is essentially we leverage this final interpretation that essentially we're maximizing some likelihood. And rather than just maximizing it over lambda, we maximize it jointly over the lambda and the epsilon. These are just two-dimensional optimization problems. I don't think they can be solved in closed form, but it's a relatively, it's not very expensive to solve this computationally compared to this step 5. Okay. So essentially, but the form of this changes a little bit depending whether real and complex. So, okay, so here's sort of the motivation. Let's look at some numerical experiments. And this first one is pretty interesting because it shows essentially what's going on. So let's take a look at a class of synthetic images, two-dimensional here. And in these images, essentially, as you can see here, it's a 48 by 48 image. There's a total of 28 horizontal and vertical transitions. So like, and then let's define alpha as the ratio of vertical to horizontal transitions. Okay, so when alpha is 1, that means there's an equal number of vertical and horizontal. In particular, there's going to be 14 of each. And that's exactly, this is just a random realization of an image that has 14 horizontal and vertical transitions located just uniformly at random. And then here's another example, just to illustrate. If alpha is the maximum value of 27, that means we have 27 vertical transitions and 1 horizontal transition. Okay. So we're going to look at these images. We're going to look at recovering these images from random phi matrices. It's sort of like a DFT with some random sign flips in between. And this is what goes on that's really interesting. So as the transition ratio alpha goes from 1 to 27, notice that the total number of transitions is fixed. Okay, so if we have an algorithm like L1 or iteratively reweighted L1, their performance does not change as a function of alpha because the sparsity, if you could say, is totally fixed. Question? Yeah, so yeah, they are separable. So the way that we're modeling them is we're using two of these analysis operators. One is just the vertical finite difference operator, and the other is horizontal. So yeah, I forgot to say that, but that's a good point. Yeah. So with both the L1 and iteratively reweighted L1, the classic algorithms, we don't see any performance difference in terms of recovery as I vary alpha because the total sparsity is fixed. And both of those penalties that they use are agnostic to how the sparsity is distributed across those two different operators. Okay. But what's interesting now is with these composite algorithms, which can exploit the fact that one operator gives you more sparse solutions than the other, you actually get tremendous gains as that difference gets large. So as one becomes very sparse compared to the other, you actually get a huge gain, in terms of the recovery SNR. So this is sort of just synthetic example to really try to see what's going on. And so that's sort of the point. There's a hidden structure here that we're exploiting sort of by this second level of modeling that looks at how we can have sparsity that varies across different subdictionaries. Okay, so now let's look at more of a practical case. We'll look at the classic Shep-Logan phantom. And using the similar randomized measurement matrix. And now for our analysis operator, we're going to look at a two-dimensional undecimated wavelet transform based on Dobrashe's 1 wavelet. And because it's undecimated, this is quite redundant. So that means that there's actually going to be 7 7 outputs for every input. Okay. And what we're going to do is we're going to split this up into 7 sub-dictionaries, and each one is going to be square. So when we run the L1 and iteratively reweighted L1, that's just going to use this big dictionary psi, but then our composite algorithms will look at each of these 7 sub-dictionaries and adjust the weights on them. And what you see is the phase transition is much, much better. So we get a huge gain in terms of being able to recover high-quality images from just a few. I think my battery died. Okay, recover high-dimensional images from just a few samples. And eventually, there's not too much of a performance difference here, but even so, and it's not only the iteratively reweighted one that has a gain over its counterpart, but also here just the composite L1 has a gain over its counterpart. Okay, so and then moving on to a slightly more realistic example here, we have a cameraman image. So this is something where when we look at it, again, using this undecimated wavelet transform, the coefficients are not very sparse. They're approximately sparse. And again here, we see these are the 2 proposed algorithms here have quite a gain over the classical algorithms, especially at low sampling ratios. Eventually, the classical ones catch up. But here at low sampling ratios, it buys you a lot to exploit differences in sparsity across dictionaries. Okay. And finally, so my co-author, he works in dynamic or medical imaging and MRI problems, and so he's especially interested in dynamic MRI. So we looked at a dynamic MRI example, and in this example, you find that the temporal dimension usually is much more sparse than the spatial ones, and so this was sort of his whole motivation for looking into these sort of techniques. So here's just an example. This is going to be, if I take a slice of this MRI movie at one time, you have a picture like this. And then if we take a vertical slice and we look at it over multiple times, you get this picture. So here you can actually see this is a blood vessel that is pulsing as time goes on. And just visually, you can see that this image here is a lot more structured. The spatiotemporal one is a lot more structured than this spatial one. Okay, so we'd like to exploit this. And we're going to use random sampling in K-space and T-space. And for the analysis operators here, we're going to use concatenation of the Dobeshi's 1, 2, and 3 orthogonal wavelets in 2 dimensions. Okay, so here what we find is, as before, we get a pretty big gain for our composite algorithms over the classical ones. Here we can see some examples of the image reconstruction. L1 looks pretty bad. Composite L1 much better. Even iteratively reweighted L1 has these artifacts here, but the composite one looks quite a bit better. Another interesting thing in this example is that there's really not much gain to doing the iteratively reweighted version of the composite one. The standard composite one does almost as well. So that's sort of an interesting observation for this particular example. And finally, what is the cost of doing this? So we have to run these iterations, so it's a little bit more computationally intensive, but at the end of the day, it's really just a factor of about 1.5 or 3 times slower. For these, we were using the Douglas-Rashford splitting, but you could use really any algorithm you'd like to do this. It's sort of independent of that. So just to conclude, so we have a new composite L1 approach to L2 constrained signal reconstruction. Both learns and exploits differences in sparsity across subdictionaries. Relative to the standard methods, we have significant improvements in reconstruction SNR, especially at low sampling rates, and the cost is just a moderate increase in runtime. So we have several interpretations of this. You can view it as a majorization minimization approach to non-convex optimization, as an approximate L0 method, Bayesian methods, variational Bayesian. So however you like to think about it. All right, thanks for listening.
Questions? So what I'm wondering, Phil, the Bayesian perspective that you provided, where the parameters are using some type of Jeffreys non-informative prior, can you perhaps explain how that could be viewed as a possible explanation about the quality of the fit of these different dictionaries to the image? I mean, is there, do you have a well understood framework for viewing this in the map framework?
I don't know. I mean, Volcon has done some work that shows that these generalized Pareto distributions are quite a good fit to natural images. So, I mean, my best interpretation is we're going to get a gain from using that distribution, but then, we also need to tune these parameters, and let's just do it in a completely non-informative way. So it could be that some other slight variation does reasonably well too, but that's my best interpretation at the moment.
Hello.
Yeah, I see.
So in one of the experiments that you showed, you considered, I think the first one, a Dobeschi filter, which you viewed as the composition of 7 smaller dictionaries. Right. I wanted to ask, what's the motivation for expecting that, if you do this, you would get an improvement?
Okay, so this is a 2D wavelet. So if you imagine you basically can divide this into sort of 4 levels. Basically, there's sort of a natural multi-resolution decomposition into 7 levels. Let me just say that, where one level is going to be the coarsest. It's very similar to this this picture I showed you here. So I think when you chop it up this way, you end up getting quite a bit of difference in sparsity across those sub-dictionaries, and that's where you get the gain. So I think like if you can choose these in such a way that you get differences in sparsity, that's what you would like to do, because that's what was suggested by this first experiment, that the bigger the difference. So here, alpha is sort of measures how much difference you have in sparsity in one versus the other. The bigger the difference, the bigger gain you get. So I think that's the motivation for chopping it up that way.
So I really like that. Can you talk a little bit more about this sort of double Pareto prior? I guess you want to get this, there's this really big literature, Bayesian literature on these kind of shrinkage priors that are kind of concentrated at 0 with heavy tails. Are you just trying to get that type of behavior, and you could use like a horseshoe or maybe even a T prior or a Dirichlet-Laplace or some other choice? Was there something really nice about the generalized double Pareto here? Or?
So we didn't really start from this perspective. We just sort of started from, I don't know, almost building a classical algorithm that looked like a lot of other algorithms. And then these interpretations came later. So it was just sort of interesting that it ends up being generalized Pareto. I guess, like it could be that you could maybe come up with a slightly different algorithm or a slightly different way of updating the weights, and it would have a different Bayesian interpretation. So yeah, I guess in principle you could try to plug in a different prior, you would get a different algorithm, and then you would have to sort of change all the interpretations that might not be as closely related to intervally reweighted L1 and so on and so on. So.
Thanks.
Okay, thank you.